In this topic, we'll look at the runtime stack, the area of memory that stores local variables and parameters for active function calls. We've looked at the runtime heap, from which dynamic storage is allocated, and we've discussed global variables. Now we'll look at where function parameters, local variables, and return values reside in memory. The simple approach might be to reserve a fixed memory location for each local variable and parameter, like we do for each global variable, each string constant in the string table, etc. This was even implied in earlier lectures, where we showed local variables residing at a particular memory location. And such an approach was in fact used in early programming languages, but it has two distinct problems. First, it's wasteful. A big program might have, say, 10,000 functions, but at any given time during the program, we're running just one function, and there is a sequence of function calls, starting at main, that arrived at the currently running function, with all the calls in that sequence waiting for a subcall to return. So perhaps main called FA, called FB, called FC, and FC is the function we're currently running. Now, these functions are the only ones whose local variables and parameters need storing, since locals and parameters only last as long as the current function call. Let's call these running or waiting functions the active functions. Even in a 10,000 function program, there are typically only a dozen active functions at any time. The storage space for the locals and parameters of the 9,988 inactive functions would lie idle and unused. And here's a quick reality check question. Only a dozen active functions out of 10,000? Why would there be so few? Think about this and answer the question, what kind of function calling pattern would be needed to have, say, 1,000 active functions? Coming back from a quick pause there, you'd need to have main call function A, which calls function B, etc., etc., a series of calls 1,000 functions deep. It's possible, but that's unlikely, except maybe if you're calling recursively, which we will discuss in the next segment of this topic, in fact. Now, the alert reader at this point may ask, well, what about static locals? Don't they have to be stored even when the function that owns them is inactive? That's a good question, and they are an exception that we'll get back to in a bit. For now, let's assume we're talking about just standard local variables. Now, the second problem with the fixed location approach for local variables and for parameters is that a recursive function will have several active instances of the same function at the same time, each calling the next. And each active call needs an independent copy of the local variables and parameters. A fixed location model can't accommodate that. So, instead of fixed locations for each local and parameter, almost every modern language reserves an area of memory called the runtime stack, which we'll abbreviate RTS. And this stores all local variables and parameters for active functions. Each active function gets space in the RTS for its parameters and locals. We've got a diagram of it here. The RTS starts with just the locals and parameters for main, as diagrammed here. In the bottommost box here in this runtime stack rectangle, we'll have main's data. The layout of the function's memory area in the RTS varies per compiler and language, but typically the parameters are grouped together, as are the local variables, somewhere in this rectangle, in other words, along with other content that we'll discuss in the next segment. Now, question 2. The code you're looking at here has been designed to show you a lot of addresses so you can kind of figure out from the output what's going on. And look at the output from lines 39 and 40, I should say, in our sample code, and answer the question, are the parameters for main, argc, argv, adjacent to each other? And are the local variables, local 1 and local 2, adjacent? And which is above, earlier in memory, than which? Is there any space between the parameters and the local variables? Moving down so it's a little more visible here, there's the output. So coming back from a pause there. The addresses for argc and argv, each of which are 4-byte values, are adjacent, as are the addresses for local 1 and local 2. The parameters are below the locals. They are higher up in memory. And it looks like about a 16-byte gap between the end of local 1 at 804 and the start of argc at 824. Of course, local 1 is 4 bytes long, remember. And there's a bit of a diagram of them in the area of the RTS for main. I won't draw boxes because we're not going to put a lot of values in there. We're just looking at where they are. Now, the area of memory on the RTS, like this one here for main, for one active function, is called a stack frame, or alternatively an activation record. The latter, by the way, is a very academic term. Using activation record in an industrial software development shop will mark you as fresh out of school. So prefer stack frame. Now, look also at the output from line 42 here. Variable global is clearly in a very different area of memory from the RTS. Globals don't reside on the RTS. They're at fixed memory locations in a separate memory area reserved for them. Okay, so now what happens if we call function FA, as we do on line 44, for instance? We need space for FA's parameters and locals while still retaining the space for main's data, which will be needed upon return from FA. So we add a new stack frame for the call of FA, putting it above the frame for main on the RTS. This stack frame exists for as long as the FA call runs, and then it goes away after the call of FA returns. In our example, as we add stack frames going upward in the RTS diagram, we're actually using lower memory addresses. Notice, this is fairly common in RTS layouts. The RTS grows from higher to lower memory addresses. We'll use the terms above and below relative to the RTS diagram, with the understanding that above actually means at lower addresses. So here's question 3. Use the output of line 9 up in FA here to tell how we should draw FA's locals and parameters within FA's stack frame, and the output of the line I'll bring into view down here on line 58. So coming back from a pause there, it's rather like those for main. The parameters are together and they're lower in the frame than the local, and there is some space between them, about like that. So what happens then when FA returns? The RTS returns to its original configuration with just main's stack frame, and main resumes its execution after the FA call. But before we show that, there are two additional details. First, FA returns a value, as you can see up here. The return statement on line 12 has to put that return value somewhere in memory. Now, in most RTS systems, the called function puts its return value at the bottom of its stack frame just before returning, and the calling function expects to see it there upon return from the called function. So, between the return from FA on line 44 of the main, this is now from the main's perspective, so between that return from that call and the assignment of the result into local 1 on that same line, 4 bytes of FA's stack frame remain as a sort of residue above main stack frame holding the return value. So let's put that return value in there. It's actually 43 as a parenthesized value since we don't really have a name for it. And let's get rid of the rest of FA's stack frame and just take main's stack frame and kind of increase a little bit, and that 43 is there at the top of the runtime stack. Okay. Now, after line 44, the return value is no longer available, and FA's stack frame, or excuse me, FA's stack frame is totally gone, and main stack frame is back the way it originally was. So, what do we mean exactly by removed? Clearly, the memory up here above main stack frame still exists, and it's not overwritten with zeros or anything like that. The running program keeps track of the location of the current stack frame, generally in a CPU register that's not held in memory at all. Let's call this the top of stack, or TOS point. During the call of FA, the TOS pointer points to the top of FA's stack frame up here. I won't redraw it all. After the call, it points to the first byte in main stack frame instead. All local variable and parameter memory accesses are made relative to this TOS pointer. So, for instance, the machine language, when we had the stack frame for FA, perhaps I will redraw it here. When we want to get to variable FA local, we look at some offset relative to the TOS rather than at a fixed memory location. And we remove a stack frame simply by changing the TOS to point to a different location. Now, the old stack frame content is still there, but it's just garbage data above the TOS pointer, which therefore we will kind of just erase. But the fact that it is still there matters in later discussion because it can be the source of interesting bugs. A brief aside here for those who may be familiar with the standard stack data structure, which has very strict access rules, in particular allowing one only to examine the very top item on the stack. The RTS is a sort of sloppy stack. It grows and shrinks by adding to the top and removing from the top, like any other stack, but you're allowed to reach down into the RTS as needed to get to any data in the topmost stack frame at any time. Okay, so now let's look at the call of FB here on line 45. Look at the addresses output from line 19 in FB, which line dumps the local variables addresses. Now, two things stand out, two questions. First, where is FB local 1 relative to the addresses of data in the prior stack frame for FA? There's our output here. Ignore FB local 2, by the way, for now. That's the next question. So, what does FB local 1's location suggest about the location of FB's stack frame? Come back from a pause there. It's in the same area as FA's locals were, which indicates that FB's stack frame overlaps the area where FA's stack frame was. This makes sense. The call of FB just adds a new stack frame above mains, using the same area as the old FA stack frame. The two stack frames don't overlap perfectly, by the way, since they aren't the same size. FB has no parameters, for instance. And then question 5 here. What about FB local 2? You can see in the output that it's at a very different address from FB local 1. Why? Is it even on the RTS? What other variable is it closest to? And again, coming back from a pause there. It's not on the RTS. It's about 2 million bytes below it. And in fact, it's in the same general area, right adjacent to, the global variable. It's a static local, remember, from the code up here. A very different thing from an ordinary local. In earlier lectures, we said that a static local is, in essence, a global variable that is accessible only within one function. And the memory layout that we see here reinforces that. Static locals are stored with the global variables. And they thus can continue to exist even when the stack frame goes away, so their values persist between function calls. Let's draw that accordingly with global and FB local down here at the bottom of our slide. Now, question 6 here. The printf on line 20 here shows that FB local 1 has the content 42. Looking down there, there it is, 42. But FB local 1 is uninitialized. So where did that 42 come from? And what does this suggest about the origin of the uninitialized data in local variables in general? Pause and think about that. And coming back from a pause, the addresses for FA local that we printed earlier and FB local 1 deserve some examination here. Let's see, there's FA local, look at that, and there's FB local 1. Okay. They're at the same memory location. And that's because the stack frame overlapping that we just discussed. It's because the two stack frames are in the same area of memory. The old garbage data from FA local shows up as uninitialized data in FB local 1. So the old garbage data from a prior call can show up in uninitialized locals in a later call. And of course, just which garbage you get depends on what was called just before you, which is highly unpredictable. Okay, so now we're going to call FA from FB on line 21 here. This adds a third stack frame for FA on top of that for FB. Thus, and we can check the addresses for FA's parameters and locals now down in this call, or this output. And you can see that they're lower in memory now than the first FA call, and thus they are higher on the RTS. So we get to question 7 here. Apparently the code to access FA local needs to go to a different memory address on each call of FA, depending on the stack frame's location. And that depends on what functions were called on the way to FA. So how does it do that? How can it know what prior calls were made each time? This is sort of an are you listening question. The answer was just discussed earlier. It's even in the diagram. Coming back from a pause there, all non-static locals and parameters are accessed relative to the TOS pointer. That always points to the top of the current stack frame, no matter where that stack frame is. So FA's machine code doesn't use a fixed address for FA local. It instead uses something like 4 bytes below the current TOS. And of course, once FA returns, we go back to just the stack frames for FB and main. Thus, and when FB returns, of course, we go back to just the stack frame for main. In general, during a long program run, the RTS constantly grows and shrinks, adding new frames as functions are called, and dropping them as functions return. And so we get to one final question 8. FB has no return statement, as you may notice up here. And yet, when we print its return value, let's see, we do that by saving it in local 2 and then printing the returns here on line 46. Apparently, it did return 43. So where did that 43 come from? And what does this suggest in general about what will happen if you omit a return statement? And coming back from a pause on that, recall that the area just above the current stack frame holds the return value from a just finished call. So line 45 right here is looking in that area for FB's return value, but FB never put anything there. So the 43 from FA's return earlier is still sitting there as garbage. If you turn on the right warning flags, a good C compiler will let you know when you've omitted a return. But it's only a warning, not an error, and it's an easy mistake to make. And the result is that you return garbage, probably a leftover return value, from a prior function call.